Let us talk about this simple string problem. We are given a string. We need to check whether the given string is palindrome or not. A string is called palindrome if you read it from left to right and also read it from right to left. You read the same string. For example, if you read this string from left to right, A, B, C, D, C, B, A. And if you read from right to left, A, B, C, D, C, B, A. Same string. So it's a palindrome. Let's now see this string. If you read from left to right, A, B, B, A. And if you read from right to left, A, B, B, A. Palindrome. Now if you see this string, if you read it from left to right, you get G, E, E, K, S. Right? If you read it from right to left, it's not G, E, E, K, S, right? It's from S, K, E, E, G. So they are not same. So this string is not palindrome and these two strings are palindrome. Now please pause this video and try to write down a function that takes a string as an argument. This function returns true if the given string is palindrome, otherwise returns false. Let us first talk about a naive method to solve the problem. The idea of naive method is simple. We take the input string, then we get reverse of the string. We reverse the string and store the reverse in a different string. So we have two strings, input string and reverse of it. Now what we do is we compare the input string with reverse of it, and if they are same, we return true, otherwise we return false. Now please pause this video and try to implement this approach. Let us now see implementation of the naive method. Here is C++ implementation and this side we have Java implementation. In C++, objects of a string class are mutable and we have reverse function which we can apply on a string. The reverse function takes two iterators. So I have passed begin iterator and end iterator, and the content between these iterators is reversed. So I will pass strings. So first I have copied the given string to the reverse, and then I have passed the begin iterator of reverse and end iterator of reverse. So this function reverses this string rev, right? And after rev is reversed, we need to check whether rev is equal to str or not. If rev and str are same, then this is going to return true, otherwise it's going to return false. Please note that in C++, when you use double equal to operator, it compares contents of both these strings. It's overloaded in the string class. Let's now see the Java implementation. In Java implementation, string is immutable. So what I've done here is I have created a string builder object, which is mutable, right? So we create a string builder, we call it rev, and we create the string builder using the given string. So it has the same content as the given string. Now the string builder is mutable and has a function called reverse. So we reverse this string builder object, and now all we need to do is we need to compare this rev with str. So we call str.equals and we compare it with the string equivalent of the string builder. So we call toString function on the string builder object. So we get a string here and we had our input string. These two strings are compared and we check whether they are same or not. So this is how we check in both C++ and Java. Let us now analyze the solutions. In both the solutions, we are creating a copy of the string, right? We are creating a reverse string here and we are creating a reverse string builder here. And this requires auxiliary space, right? And then we are comparing reverse and the original string one by one. So it's going to take theta n time, because you will always do the reverse. Whatever string you are provided, you are always going to traverse through the whole string and then you are going to reverse it, right? Also it requires theta n auxiliary space. So theta n time and theta n auxiliary space, right? And this is how it works. You are given a string, you reverse it, right? And you compare string and reverse, and this much is the time and auxiliary space required by the solution. Now please pause this video and think of a solution that works with theta 1 auxiliary space and is big O of n. So it might work in constant time in some cases, and n is an upper bound, not the exact bound. Here it is theta n. So the solution that I am going to talk about is better, because in the worst case it will take n and in the best case it will take constant time, and it takes constant extra space. Let us now talk about the efficient solution. The idea of the efficient solution is first compare first and last characters. For example, if this is a string, you compare this character with this character. And if these characters are not same, then your string cannot be palindrome. And if these characters are same, then you go ahead and compare these two characters. You mainly begin two indexes. One starts with the left side and the other starts from the right side. You compare the characters at the begin index and the end index. If they are same, then you move ahead the begin index and you decrease the end index. So now your next characters are these two. If they match, fine, otherwise return false. And if they match, then what are you going to do? We are again going to move these begin and end index one position ahead. So begin also comes here and end also comes here. And begin and end, when they become same, it means you have one character left. So you can return true. Now there might be one other case when begin and end do not become same, and that other case would be in case of even sized strings. Let's take an example of even sized strings. Let's say our string is CBA. Now we'll again begin from this side and we'll begin from this side. We'll compare begin and end, they are same. So we'll come here. Right. Now we'll compare begin and end, they are same. So we'll come here. Now we'll again compare begin and end. Right. This is our begin and this is our end. They are same. So we'll move ahead. Now what will happen when you move ahead? Your end is going to come here and begin is going to come here. So when begin and end cross, then you also return true, right? That's the simple idea. Now please pause this video and try to implement this idea. Let us now see implementation of the efficient approach. So I've written a function spell in Java and spell in C++. We pass a string argument. In Java it's by default by reference. In C++ I've used ampersand to pass by reference, because if I don't pass by reference then a string will be copied. That would cause unnecessary copying of the strings. So once we receive the string as an argument, we initialize our begin with 0 and end with last index, and last index is string length -1. Now we run a loop and this loop runs while begin is smaller than end. See, if begin becomes equal to end, then your string is odd length string and you've reached the middle character, you should return true, right? So we come out of the loop and we return true. And if begin and end they cross each other, then also you have traversed through the whole string, you matched every character, you come out of the loop because begin and end they cross and you will return true. Now what do we do inside the loop? We compare the character at the begin index and at the end index. If they are not same, then we return false immediately. So we start traversing from both the ends. If they are not same, we return false. If same, then move ahead. To move ahead, we do begin ++ and end -. And we again compare. If they are not same, then return false. If same, then move ahead, move ahead, move ahead. If it's an odd length string, then begin and end would become same, and you will come out of the loop and you will return true. If this is an odd length string, then begin and end will keep on moving toward, and if the string is palindrome, then they will reach the same character, middle character. You will come out of the loop and you will return true. And if it's an even length string and if it's a palindrome, then begin and end cross each other and you will return true. Now what is the time complexity of the solution? We are traversing from both the sides, so every character is being compared at most once, right? If it's not a palindrome and if say corner characters are themselves not matching, then it's going to return in big O one time, constant time. And in the worst case, when the string is palindrome, then every character is being compared at most once. So it's theta n in the worst case and theta 1 or constant in the best case. And in general, we can say it's a big O of n algorithm. Big O of n covers both worst case and best case. Worst case it's theta n and best case is theta 1. And how much auxiliary space it requires? It requires constant extra space. So we can say big O of 1 or theta 1. See, constant can be represented by either big O of 1 or theta 1. And when we write big O of n, it means it's upper bounded by n. It can take less time, and that's the situation here. This program might end with in constant time if the last two characters themselves do not match.